Hello everyone, this is Ankita Rajput and today this is our lecture 5 of solid state physics. So now we will discuss few important things like phonons. We will discuss about the lattice heat capacity and all the three theory, classical, Einstein and device theory of lattice heat capacity. Okay, and then we will discuss some previous year's problems. So yeah, so first we will discuss about phonons. So as you all know about photons, right? So photon is nothing but it's basically a quantum of electromagnetic energy. Okay, so in the same way, as we all know that in crystal there are some lattice vibrations, okay, and due to these lattice vibrations we have some lattice energy in the crystals, okay. So this lattice energy, or we can say the elastic wave, is also quantized, okay, and the quantum of this vibrational energy is called phonon, okay. So we have some important points about phonons, like if the vibrations are produced due to some thermal energy, so these phonons are known as thermally excited phonons, okay. And if the vibrations or waves are due to some sound waves, so they phonons are said to be acoustical phonons, okay. Similarly, if the excitation or vibrations are produced some optical phenomena, okay, so these phonons are known as optical phonons, okay. And there are so many concepts, so many we can say assumptions which are true for photons are also valid for phonons. So like the famous wave particle duality principle, which is applicable on photon, it's also valid for phonons, okay. So the energy of phonon is h cut omega, okay. If we can say omega is the angular frequency of a mode of vibration, so in that case the energy of a single phonon will be h cut omega, okay. And if in a particular mode of vibrations, if we have n number of photons, okay, n number of phonons, so in that case the total energy will be equals to n h cut omega, okay. So we can also calculate the average number of phonos in a vibrational mode, okay. We will use the Planck's distribution law, or by using this law we can calculate the average number of phonos, and it's basically 1 upon e to the power h cut omega upon kbt minus 1, okay. So this is the average number of phonos, and kb is nothing but Boltzmann constant here, okay. And one more important thing about phonos are basically indistinguishable, okay. And if they are indistinguishable, so that means they follow Bose-Einstein distribution function, okay. So physically, phonons, they don't have any momentum, right? But they interact with other particles in this way that shows that they have a momentum, okay. And the momentum is h cut k, okay. And this h cut k, which is basically the momentum of photon, is also known as crystal momentum. Okay, so now we will discuss the specific heat. Okay, so as you all know, it's a very common topic in schools. Like specific heat is, it's basically the amount of heat that is required to raise the temperature of 1 gram of substance through 1 degree Celsius. Okay, so and it's C is basically dq over dt or dE over dt. So this dq or dE is nothing but the required amount of heat to raise temperature from T to T plus dt. So as we are talking about solids, okay, so in the case of solid, the specific heat of solid is the combination or the addition of two different specific heats. So see, solid is basically the sum of lattice heat capacity, that is C lattice, and electric heat capacity, means C electric. So this C lattice is known as lattice specific heat, and it's due to the atomic vibrations, okay. And this C electric is the electronic specific heat, and it's due to the electronic system, okay. So in solids we have two types of specific heat, okay. And one more thing, in solids we use term heat capacity, okay, not specific heat more frequently. So this heat capacity is basically the heat required to raise the temperature of complete mass, complete substance, okay, through 1 degree Celsius. So we can relate this heat capacity with specific heat. So the heat capacity is the specific heat per gram or per unit volume. So this is how we can relate specific heat and heat capacity. So these are the experimental facts about heat capacity. Okay, so at room temperature, if your substance is at room temperature, so heat capacity is nearly 3 nkb. Okay, n is the number of atoms and kb is Boltzmann constant. Okay, so for 1 mole you can calculate heat capacity and it will be 3 nakb, and Na here is Avogadro number. So this nakb is R, and the R is gas constant, and the value of R is 2 calorie per mole Kelvin. So your heat capacity will be 6 calorie per mole Kelvin. Okay, this is at room temperature. Okay, but at a low temperature, when we can say T tends to 0, your heat capacity decreases sharply and it follows TQ law. Okay, and this law is for insulator and T law for metals, but in solid, most of the solids obey this TQ law. Okay, so these are the experimental facts about heat capacity. So now we will see, using theoretical assumptions, we will see, okay, what is the heat capacity. So first we will discuss about the classical theory of lattice heat capacity. Okay, so in this theory we assumed that in our crystal we have number of atoms. Okay, and these atoms behaves as three-dimensional harmonic oscillator. Okay, because atoms are vibrating, so these are basically harmonic oscillator according to classical assumptions. Okay, and they all atoms vibrate independently. Okay, and they vibrate with same natural frequency omega naught. Okay, and their energy can be different because they vibrate with different amplitude. Okay, so if we have three-dimension harmonic oscillator, so you can calculate the thermal energy, average thermal energy of these harmonic oscillators, and the energy of a single harmonic oscillator is kT, and as we have three-dimensional harmonic oscillator, so the energy will be 3 kT, and if we have n number of such oscillators, so total energy will be 3 nkBT. So this is the average thermal energy, and from this formula we can calculate the heat capacity of solid. Okay, using this formula, so your heat capacity will be 3 nkb and 3 nkb, and we can calculate molar heat capacity, so it will be 3 nakb, so similarly it will be 3R. Okay, and the exact value will be 5.96 calorie per mole Kelvin, and it will be nearly equals to 6 calorie per mole Kelvin. So this law is known as Dulong-Pettit law, when your specific heat is independent of temperature and it's a constant. So it's a Dulong-Pettit law. It's a famous formula. Okay, so that means your heat capacity is constant and independent of temperature. Okay, in classical theory. So this theory is failed completely because it could not explain the heat capacity at low temperature. Okay, so if you see this graph, this is the graph between heat capacity and temperature for three different substances. Okay, silver, germanium and silicon. So if you see at high temperature, uh, the value is nearly 6 calorie per mole Kelvin. So we can say at high temperature, classical theory is okay. It can explain the specific heat or the heat capacity, but at low temperature it couldn't, because according to experimental results at low temperature it should follow TQ law. Okay, so this theory is failed, and this the problems was resolved by Einstein and Debye theory. So now we will see how. So in Einstein theory of lattice heat capacity, we have some important features like a crystal. As you all know, a crystal consists of atoms, and these atoms can be regarded as identical and independent harmonic oscillators. So this assumption is same as in case of classical theory. and all the oscillators vibrate with same natural frequency omega naught. This assumption is also same. These oscillators are quantum oscillators and have discrete energy spectrum. So this is the main difference between the classical and Einstein theory of lattice heat capacity. Here we consider the oscillators as quantum harmonic oscillator, and we can have number of oscillators, different number of oscillators in same quantum state. Okay, and these oscillators obey the Maxwell-Boltzmann distribution of energy. So using these assumptions in this theory, we calculated the internal energy of the whole crystal, and this is the formula. So we are not going in detail about the derivation, because derivation not important, the result is important. Okay, so internal energy will be 3 by 2 n h cut omega naught plus 3 n h cut omega naught upon e to the power h cut omega naught kt minus 1. So this is the internal thermal energy. So we can calculate the lattice heat capacity by using this formula. Okay, Cv equals to this. So it will be 3n kb h cut omega naught kt square e to the power h cut omega naught upon kbt and upon e to the power h cut omega naught upon kbt minus 1 to the power ka whole square. So here this term h cut omega naught upon kb is theta e. Okay, so theta is the Einstein temperature, so we can convert this in terms of theta e. So the final formula of lattice heat capacity will be this. So this is very important formula. Okay, so now we will. Okay, so at high temperature, our specific heat is 3R. Okay, so we can say it is following your Dulong-Patis law at high temperature. So now we will see at low temperature, okay, what is the behavior of this lattice heat capacity at low temperature. So at low temperature, this term KT will be very less than h cut omega naught. Okay, so your okay, or we can see I think we missed something. Okay, that t will be very less than theta e. Okay, so this term, the exponential term e to the power theta e t minus 1, this term, okay, so it will be, we can say we will just take two terms, okay, and it will be e to the power theta e upon t. Okay, so we can again put here these terms like this. Okay, and finally we will get this Cv. Okay, so this will be your Cv. Okay, so heat capacity here is proportional to these terms, e to the power minus theta e upon t, theta e over t ka t to the power square. So experimentally we are getting that at low temperature our lattice heat capacity is proportional to T cube, but we are not getting the same result here. So that means we can say that at low temperature this theory, Einstein theory, is also failed. Okay, and also you can see this graph. This graph is between the theoretical heat capacity of diamond and Einstein model. Okay, so we can see the difference, the comparison between the Einstein model, Einstein theory, and the classical theory. Okay, so we can say that Einstein theory provides a better explanation, as we see, as compared to your classical theory. Okay, but your the reason is here okay, you can see this behavior. Okay, so this is the theoretical curve. Okay, so one more important thing is there. Here you are getting these results at low temperature, these results, and okay, and this is drastically different if we compare the result with your experimental results. So the main reason is that in this Einstein theory, what you considered that your atomic oscillators, they all are vibrating independently with a particular frequency omega naught. Okay, but this is the wrong statement. This is the wrong assumptions, because in crystal we have atoms, right? And all the atoms are vibrating, and they are basically, when they are vibrating, so somehow they will be coupled together. And if they are coupled, these atoms are coupled, so there are number of possible vibrational frequencies, okay? And we cannot say that there is a particular single frequency, okay? They all are coupled, so due to this coupling we will have a different vibrational frequencies, okay? So this is the correct assumption, and this assumption is taken into account by your device model, okay? So this is the we can say this is the model, and they use this assumptions. What assumptions means? We have a crystal, okay, and we have so many atoms inside the crystals, and so many we can say atomic oscillators, harmonic oscillators. So this system was considered equivalent as a vibrational motion of system of coupled harmonic oscillators. So this is the thing we are saying, that all the harmonic oscillators here basically are coupled, okay? So they can produce a range of frequencies, okay? Means a range of frequency, so that there will be different modes of vibrations, okay? And the number of vibrational modes per unit frequency range is known as density of modes, okay? So this is the assumption. You need to figure out what are the assumptions, what are the basic concepts are taken by classical theory, Einstein theory, and your divide theory, okay? And now we are talking about the density of states. So first we will calculate density of states, density of modes actually in device model. And this density of mode is nothing but basically the number of vibrational mode per unit frequency range. So first we will calculate this, then we will calculate our lattice heat capacity. So how we can calculate the density of modes? So the possible number of modes of vibration for a cube of length L in frequency range nu to nu plus d nu. So in density of states, first we will take a single string, okay, in one dimension. And in one dimension case, we will calculate the density of modes, okay. And similarly, for the result, we will take the result and apply the result for a cube, okay, of HL. And now we will see, we can calculate actually, but we are not giving you the whole the derivation, okay. I'm just giving you the result. So your density of modes in 3 dimension will be Z nu d nu equals to 4 pi V upon Vs cube nu square d nu. So this V is the volume. We are taking cube of length L. So V will be the volume and V will be L cube, right? And this Vs is the velocity of the wave which are propagating, okay. And this is Vs, means S is because of solid. We are talking about solid, okay. And nu, we are calculating these modes, density of modes in frequency range nu to nu plus d nu. So nu is your frequency, okay. So yeah. So in solid, basically we seen that there are two types of modes, okay. There are two types of modes of vibrational modes, longitudinal and transverse modes, okay. So we need to take two different these velocities, okay. One for longitudinal mode of vibration, and second due to transverse mode of vibration, okay. So we need to take Vt and Vl. And second thing is that the transverse waves have two vibrational modes, okay. So we will take two. So for whole solid, we will take these two things, Vt and Vl. So our density of modes will be 4 pi V 2 upon Vt cube plus 1 upon Vl cube nu square d nu. So this is the final density of states for your solid material. Now, the main thing is that Debye, what he did, he take a approximation, okay. And what is this approximation? He said that in your solid, in your crystal, we have fixed number of atoms. We have fixed number of atoms and inside your crystal. And we are saying that there will be different modes of vibrations, different frequency inside the solid. But we need to take up approximation, means we are restricting that there will be a certain number of frequencies and up to a maximum frequency. And why we are taking these assumptions? Because here we have only n number of atoms inside the crystal, means 3n harmonic oscillators. So for this we take the maximum frequency nu d, okay, which is also known as Debye frequency, and we take this we put this restriction, okay, means your density of modes, if we integral this, it will be equal to 3n. Okay, so we can put the value of z nu here. Okay, so now we can calculate the vibrational energy of the crystal. And what would be the energy? What is the formula of this z nu? This is the density of, you are listening, guys?
Yes, ma'am. 4 pi V upon Vs cube V square into dV.
Yeah, but yeah, right. But in generally, what is this? Energy per unit frequency range, right? So if we have the
Yes.
if we have this z nu, we can calculate the total vibrational energy. Okay, and what we need to do, we just need to multiply this term by the average energy. Okay, the average energy, so we can calculate the whole energy of the crystal. And how we can take this value E bar, it's the average energy of your oscillator. And we can use what is this relation? You know this formula, right? I know today it's a theoretical part, we can say, and but it's not that much boring. You are not answering, means you are not listening properly. Hello, guys.
It's about internal energy of crystal.
Okay.
From the phonon.
Hasmukh is speaking?
Yes, ma'am.
Okay. Okay. Aarti, Shravya, Arya, Harun. I want answer from everyone. From now onwards, now I will do one thing. When I'll ask questions, now I will ask you to switch on your video mode. You listening?
Okay,
no one is answering except Hasmukh.
No, ma'am. We are here.
Yes, ma'am. We are listening, ma'am. Actually, it is not clear to me.
Okay. And what about the rest, guys? If we will not we can say ask something, na, you maybe you can sleep sometimes.
I hope we are there.
It's nothing, it's Planck's distribution law, and using Planck's distribution law we can calculate the average energy of oscillator, na? Okay, so it's this formula, E bar equals to HQ over e to the power h nu over kt minus 1, and it's all already written. You can also relate using Planck's theory, we written now. So this is the Planck's distribution law, and using this law we can write the average energy of oscillator, and this is this, and we can put this value of E bar here and also the value of this Z nu. Okay, and we can calculate the internal energy, the vibrational energy of your crystal, and this is this. Okay, and also we can calculate from E, what we can calculate, the specific heat CV, that is del E over del T. Okay, so this is your lattice specific heat. So this term theta D is device temperature, and its value is h cut nu over kV, h cut nu d over kb. Okay, so we will also imply the two conditions means at high temperature first we will calculate, then at low temperature. So at high temperature your T will be very greater than theta D. Okay, and this is your formula. This is your formula, these two formula. So if your T is very greater than theta D, you can convert that your E will be this. Okay, and you can calculate this value. Okay, this integration is simple. So your E will be 3 N kBT. So you can calculate CV, differentiate this term with respect to T. So it will be 3 N kB means 3 R. Okay, so at high temperature in device theory also, our lattice heat capacity is constant and equal to 3R, means it's following Dulong's Pettit law at high temperature. And what about the low temperature? For low temperature, we will use this thing. T will be very greater than theta D. So put these things. Okay. So your E will be this term. Means your energy is proportional to T to the power 4. And guys, tell me, if our thermal energy is proportional to T to the power 4, what is the law called?
I don't know about
If E is proportional to T to the power 4, the law is called what?
Ma'am, I don't remember actually.
Do you know there is a law known as Stephen's law?
Yes, ma'am.
What is the law?
Stephen's Boltzmann.
E to E equals to sigma T4, right? Okay.
Yes,
so,
ma'am. Yes, ma'am.
So here we can say this is, we can say is similar to that law. Means E proportional to T to the power 4. So we can calculate CV from this. Okay. So your CV, just differentiate this term, and your CV will be proportional to T to the power 3, because other terms are constant. So at low temperature in device model, our lattice heat capacity is basically proportional to T cube, means it matches the experimental results. Okay, and this law is also known as T cube device law. Okay, so it means your device model successfully, we can say, match the experimental results. Okay. So these formula, guys, these formula of lattice heat capacity in these three classical theory, device theory, and in Einstein theory. Okay, at high temperature, at low temperature are very important. Okay, so just check your previous year question paper. You will find many questions based on these results only. Okay, not about the derivation and all these things. So that I didn't mention these things. Okay, we just discuss the results. So these are the few problems. So everything is clear, guys? Any confusion so far?
No, ma'am.
Yes,
okay.
No doubt.
Okay, good. Okay, you don't have any query now. So I'll ask you in next lecture. Okay, and you have to answer. So
Sure, ma'am.
yeah, great. So this is from NET December 2014. It's very simple. So consider two crystalline solids, one of which has a simple cubic structure and the other has a tetragonal structure. The effective spring constant between atom in the C direction is half the effective spring constant between atom in the A and B directions. At low temperature, the behavior of the lattice contribution to the specific heat will depend as a function of temperature Ts. Tell me the right answer. It's very simple. Read the question once and then tell your answer.
No. I think B is correct answer.
You think B is correct? Solid. Okay.
Yes,
and
for both.
okay,
A
and
and B.
okay, and others?
Option C, I guess.
Okay. And who is speaking? Harti?
Yes, ma'am.
Okay. And Shravya? Harun? Arya? Please, guys, answer. Pearl is also there. If you don't know the answer, you can tell me that you didn't get.
I'm option D, T cube for both, sir.
Who is speaking?
Pearl.
Pearl. Okay, Pearl. Okay. Next, Shravya, you there? Not there. Harun? Not. Okay. So, Pearl, you are right. Okay. So, I will tell you. Okay. So, first, we will take the wrong answer. Justin, you said, Hasmukh, you said B. T for the tetragonal solid and S TQ for the simple cubic. You said D? Okay, no issue, guys.
Yes, I said D, T cube for both.
Okay, that's good. Okay, so see the question. Okay, one thing, guys, in net examination, especially in net examination, okay, always, it's the case always, if a problem is very, very lengthy and there are so many stuff available, so many different concepts, and you are getting confused, okay, so need to follow the basic things only. Okay, you need to answer the specific heat first. Underline this thing, specific heat. Okay, lattice, and lattice is there, means we are talking about lattice specific heat, and we just read about the lattice specific heat. We just discussed that at low temperature, okay, at low temperature they are asking now, at low temperature what is the trend of lattice specific heat? It's proportional T cube. We didn't mention anything about the simple cubic and anything tetragonal. Okay, we didn't mention that it should be different for different kind of crystal structures, right? For all solids, we calculated that at low temperature, our lattice specific heat is proportional to T cube, right? So for all the solids, if it's tetragonal, if it's BCC, if it's anything else, okay, your lattice specific heat in all the cases will be proportional to T cube at low temperature, right? But one more important thing.
Ma'am, please explain it
Okay.
again.
Okay. Okay. In last slides, what you see, guys, what you see that we discussed with you first thing that experimental results shows about the lattice heat capacity, means the heat capacity or specific heat of solids, that at low temperature it depends on T cube. At high temperature is 3R. Okay, remember always these things. So now they are also talking about solid, and they are also talking about lattice specific heat, and they want to know that at low temperature for these different structures, tetragonal, BCC, okay, at low temperature what would be the relation, what is the dependence of T? Okay, so it whatever the crystal structure once, because we are discussing about in the whole PPT that all the solids, okay, all the solids at low temperature, experimental results, I'm talking about the experimental results. Okay, so lattice heat capacity is proportional to T cube at low temperature. Okay, so this will be the right answer. Okay, but one more important thing, the whole scenario we discussed is only about 3-dimension, is only about 3-dimension. So yes, in 3-dimension, it depends on this T cube, because we are talking about crystal structures. So your tetragonal, your BCC structure will be in 3-dimension only. But if we talk about, if in question it is given that you are talking about the specific heat in 1-dimension. So in 1-dimension, it will be proportional to T only. Okay, and this is 2. I forgot to mention, I will correct. Okay, so in 2-dimension, this specific heat will proportional to T square, and in 3-dimension, this is 3. Okay, let me correct. Okay. This is 3. Oh, sorry. Shit. Okay, you are getting now what I'm saying. And this
Yes,
is
ma'am.
okay, and this is 2
Yes.
actually. Okay, so remember this thing. Okay, I highlighted this term. In 1 dimension, your specific heat will be proportional to T only. In 2 dimension, it will be proportional to T square, and T cube. This is the case in 3 dimension. Okay, guys.
Okay, ma'am.
Yeah. This is GATE 2012 problem. Which one of the following cannot be explained by considering a harmonic approximation for the lattice vibrations in solid? This is also very, very simple. Just tell me the answer. I will also tell you the answer, but it's always best you need to process things. That's why only that you can understand how to process the questions in examination.
Ma'am, I don't know about optical branches in lattice. What is this? I don't know.
You didn't attend the last lecture, last lecture, when we discussed about
Yes,
the
ma'am, I
lattice
did.
vibrations.
Yes, ma'am, I attend the lecture.
We discussed about the acoustic.
Okay,
acoustic.
okay.
Yes.
Yes, ma'am.
Aarti
Okay,
Shravya par. Dekho, look. Which one of the following cannot be explained by considering a harmonic approximation for the lattice vibrations in solid? Okay, they are talking about lattice vibrations, and what we can calculate using lattice vibrations, lattice heat capacity, right? If we calculated lattice heat capacity, so this is the result of the lattice vibrations in solid, right or wrong? No answer. Okay, so device T cube law.
right.
Divide to T cube law. What we calculated using this law, lattice heat capacity. Dulong-Pettit law. It's also about the heat capacity. Optical branches in
Also,
lattices. We are also talking about
right.
lattices. Okay, and lattice. This term is common. So thermal expansion. What is a thermal expansion? You read this term. You know, you are familiar with this term, thermal expansion.
Yes, ma'am.
In 9, 10, 11, 12, you already know this term,
Yes,
thermal
yes,
expansion. So this is a basic term, thermal expansion. So it's not related at all, basically, from these thermal vibrations. Okay. So this is the odd term. This is the odd term. Sometimes we need not to go in very much detail. What we read in Dulong-Pettit law, in this, we just need to figure out the very common things. Okay, so thermal expansion, this is the correct answer. Okay, the last problem. In order to estimate the specific heat of phonons, the appropriate method to apply would be, okay, this is, I will tell you. So, one thing guys, you need to remember that your device model, your device model is basically for the acoustical mode. Okay, you need to remember, this is some advanced thing, but you need to remember once we talk about the device model, there is also some limitation in device model. Okay, I will discuss in next lecture few failure of this device model. So is this model is basically suitable for the acoustical branch, means the waves, sound waves. Acoustical means nothing sound. So this is for sound waves. So this can we can say explain these things. And your Einstein model it is best suitable for optical mode, because this model is only valid for high temperature. For low temperature it's failed. So due to this reason, this Einstein model is only suitable for optical phonons. Okay, means the phonons which are generated due to the optical phenomena. Okay, and this Debye model is only valid for acoustical phonos. Okay, so this option B is correct option. So you need to remember these things now. Okay, any doubt, any confusion?
No, ma'am.
Okay,
No.
okay, good. So okay, no issue. So we had already 5 lectures of solid state physics. Okay, on Saturday we will have our next lecture. Okay, and guys, your quiz, it's helpful for you?
Yes,
Yes,
ma'am. Very
ma'am.
good.
Okay.
मैम ये सभी सब्जेक्ट के लिए हो सकती है क्या क्विज
नहीं,
हमारी?
सभी के लिए ही होगा, अभी सभी
हाँ.
के लिए ही होगा. आई थिंक now maybe next week na you will have a quiz for mathematical physics, and in the
Okay.
same week for thermodynamics also. Okay, so you need to prepare simultaneously. आपको जैसे पीडीएफ जैसे भी कोई लेक्चर हो जाता है तो यू नीड टू रिवाइज ऑल दीज थिंग्स. ओके, क्योंकि आप लास्ट में आप करने बैठोगे तो इट वुड बी वेरी वेरी डिफिकल्ट फॉर यू. ओके, so
Okay, ma'am.
okay, you have time guys. So once we had a lecture, once we finished, we will upload all these things. Okay, so just download from there and read all these things, and also books, referred books also. Okay, so and also I asked you, said that you should collect the queries, the problems in previous year's question papers. Did you guys try?
Yes, ma'am.
Okay, from okay, no issue. Okay, so see you in next class. Okay.
Okay, ma'am.
Okay, yeah, bye bye.
Thank you,
Thank you.
ma'am.
Bye,
Thanks.
ma'am. Thank you, ma'am.
Thanks.